In this video, what we are going to do is we are going to prove at least most of the change of variables theorem. We're going to do this in several pieces. So let's remind ourselves of what this says. X is a compact Jordan domain in Rp. Compact Jordan set, and we let G be an open superset of X. And we let phi be a continuously differentiable. It is an exercise that I will leave for you that the determinant function is continuous. So the function, if f of x is the absolute value of the determinant of this derivative, d phi of x, then f is continuous on all of g. In particular, it is continuous on an x. And so, as a note, but a theorem 7.2.13, f is integrable. On x. And now we remember that we said the full theorem says that phi of x is a Jordan set. The image of phi is Jordan, and in fact, you can write its volume as the integral of this function x. The part one, what we're going to prove first is the following. If epsilon is a positive number, then there is a rectangular cover P of x such that the upper Darboux sum of 1 over p is less than or equal to the integral. The integral of f, I'll write it out one more time. Plus our small error epsilon. We will, of course, prove a similar result for the lower Darboux sums, and then once you put those together, you see that phi of x is a Jordan set with the correct volume. So here is the first step of the proof. First, we saw that f, that's the determinant of d phi, is integrable. So that means, in particular, there is a rectangular cover Q1 of x. We're going to refine this several times such that the upper sum of our function f over the cover Q1, that's less than or equal to the integral over x of f dv plus epsilon over 2. You can get upper sums as close to who the integral is you want, how close I want is epsilon over 2. We may also assume that we can also require that every rectangle in Q1 have positive volume. You just do the same thing within epsilon over 4, or in place of epsilon over 2, and then you make all of your rectangles of volume 0, you make them just a little bit bigger so they have positive volume, and you can do that in such a way that you're adding less than epsilon over 4 to the upper sum. Now we're going to use a whole bunch of results from our section on compactness. First off, X is compact. G is open, and X is a subset of G. So by a not terribly difficult exercise in section 5.5, there is a positive radius R such that if X is in our set X, then the ball centered at X of radius R is contained in G. G is open, so for every point X in X, you can draw a ball of radius R or around X, where R depends on X. And the compactness means you can get rid of the dependency on X. There's one positive radius that will work for every X in the set. And then Q1 is a cover of X. So that means it's a bunch of rectangles. If you've got a rectangle, you can refine it into finitely many smaller rectangles whose diameter is as small as you want. You just cut it up as finely as you need to, and then the biggest diameter, that's the biggest diagonal, you can make it as small as you want. So that means there is a refinement of Q1. Such that every rectangle in Q2 has diameter less than that radius, little r. And now, just in case, we're going to let Q3, we're going to throw away all the rectangles that don't actually intersect X. We're going to throw away all the superfluous rectangles. All right, and notice if you go back to section 7.2 and look carefully at the definition of refinement, you'll see that Q3 is in fact a refinement. Of Q2. It's still a cover. The only rectangles we threw away were the ones we didn't need to cover X. It's still a collection of non-overlapping rectangles, and every rectangle in Q3 is a rectangle in Q2, so it's contained in a rectangle of Q2. Now let's let K be the union of all the rectangles in Q3. And then K is the union of finitely many rectangles. They're all closed and bounded. So K is compact. Exercise 5.5.1 says the union of finitely many compact sets is compact, or obviously now the union of finitely many closed bounded sets is closed and bounded. Also, if R is in Q3, then there is a point X that's in both R and our set X, and the diameter of R is less than R, so R is contained in the ball centered at X of radius little r, which is contained in G. So the upshot is that K is not only compact, it is contained in G. Also, just in case it needs saying, X is contained in K, which is contained in G. K is a compact set between X and G. Now, let's recall we said phi was continuously differentiable. You can think of the function d phi. It is a function who takes as inputs points in our open set and spits out linear operators. And by continuously differentiable, we mean that function is continuous. So by theorem d phi is uniformly continuous. On any compact subset on X, but we actually need it to be uniformly continuous on K. Also, the function, the norm function, a norm in a vector space is always continuous. So this is a continuous function. You can think of the norm of A as the distance from A to 0, and if you fix a point in a metric space, the distance to that point is continuous by an example we saw back in section 5.4. So the following function, g of x, is f was the determinant of d phi of x, g is the norm of d phi of x. It's the composition of two continuous functions is continuous on G. So by the extreme value theorem, it has an upper bound. It is bounded on K. There is a real number m. It's less than infinity, I want to emphasize, such that d phi of x, the norm of that, is less than or equal to m for all x in K. Let's get back to uniform continuity. Remember, uniform continuity says for every epsilon, every positive epsilon, there is a delta such that if x minus the distance from x to y is less than delta, then the distance from d phi of x to d phi of y is less than epsilon. Now, I'm already using epsilon to mean something in this problem. I don't want to use it again, so I'm going to use the letter E instead. Let's let E be whichever of these two things is smaller. M over 2. M is the maximum value of d phi. And then the epsilon we've already defined. And then the denominator, this is going to be a mess. We'll see why we want this denominator going on. So we've got epsilon over 2 to the power of 2p plus 3. That's 2 to a power depending on your dimension. Then p, your dimension, 2p over 2. Then your constant m, your upper bound on the d phis. Then there's the upper sum of 1 over the rectangular cover Q3. Why don't I go ahead and add a 1 just to be absolutely sure I'm not dividing by 0 here. And then our d phi is uniformly continuous on K on all the rectangles in Q3. So there is a positive number delta such that if X and Y are in K, and in particular if they're in the same rectangle, then the distance, that's the linear algebra norm from d phi of X to d phi of Y, is less than that long complicated number E above. Now we are going to refine Q3 yet again. And I'm going to ask for the following 3 properties. First of all, we're going to say we want all the rectangles in Q4 to be small, to have a diameter less than delta. So in particular, this condition is true for any 2 points in the same cube in Q4. Next, we want all our rectangles to be nice rectangles. Meaning the shortest side is at least half the length of the longest side. And for simplicity, we'll go ahead and throw away any superfluous rectangles. Note that in particular, if C is in R and R is in Q4, then R is contained in one of the rectangles in Q3, and also diameter of R is less than delta. Every point in R is within delta units of C. Then the supremum over all points Z and R of the distance from D E of Z to D phi of C is less than our number E. Now notice Q4 is a refinement of Q3, which is a refinement of Q2, which is a refinement of Q1, and refinement is a transitive property. So by a very early proposition in section 7.2, we have that the upper sum of f is the absolute value of the determinant of d phi that I don't feel like writing out anymore. That's less than or equal to the upper sum of f over q1, because q4 is a refinement. Refinements just pull your upper sums down. That's less than the integral over x of f dv plus epsilon over 2. That's how we picked q1. And because every rectangle in q4 intersects x, we can notice that this upper sum is in fact the sum over the rectangles in Q4 volume of R. Also notice we have that Q4 is a cover, so X is contained in the union of the rectangles in Q4. So phi of x, the image of x, the set we're trying to show is Jordan. That's contained in the union of the images of the rectangles. One piece of notation for each rectangle in Q4. Let's pick a point. C in that rectangle. You can pick the midpoint, you can pick the point where f is maximized, you can pick the point where f is minimized, whatever. Just pick one of the points in each rectangle. Now let's remind ourselves of the proposition and the lemma we proved in the last video. I've written this a little bit more or simply instead of the supremum over the rectangle. D phi of z minus d phi of c. I'm just writing an e here and here, but we saw that that's an upper bound. So we know something about the images of our rectangles. So we know in particular, by the proposition, phi of x is contained in the union of all the rectangles in Q4 phi of r, but by the proposition each of the phi of r's is contained in some Jordan set, different Jordan set for each rectangle. So I'll call it J sub r, where J sub r is Jordan. And by the lemma, there is a rectangular cover. P of E of x, y here is our phi of x here, such that the upper sum of 1 over p, remember the theorem we're trying to prove is all about the upper sum of 1 over p, it's less than epsilon over 4 plus the sum of the volumes of our Jordan sets. So now we just need to look at the volumes of our Jordan sets. Let's recall some notation. F of C is the absolute value of the determinant of d phi of C. And I'm going to need some shorthand. Let's let gamma be the norm of d phi of C. And since C is in a rectangle, that's less than or equal to the biggest this norm gets anywhere in K. So this is less than or equal to our constant M that we found before. And by the proposition, the volume of our Jordan set JR is less than or equal to the volume of R times F of C plus the diameter of R to the pth power. And then we've got our gamma plus 2e to the p minus gamma to the p plus e to the p. Let's work out what that thing in the brackets is. This is an induction argument. I'll leave it to you to work out the algebraic details to check that this is correct. If p is equal to, say, 1, and to show that the induction works, it's equal to gamma to the p plus 2 times e, sum from I equals 0 to p minus power of p minus 1, gamma to the power of I, and then gamma plus 2e. Actually, let's make gamma plus 2e have power I and gamma have power p minus 1 minus I. So the thing in the brackets subtract off a gamma to the p, add an e to the p. That is, the gamma to the p is, of course, are going to cancel. So we're left with 2e actually, let's make this a less than or equal to, let's notice that gamma is less than or equal to our big M. And then gamma, and then 2e by assumption is also less than or equal to big M. And then our e to the p is less than or equal to, it'll make the algebra a little easier in a moment. If I make this 2e times m to the p plus 1, we can factor out a 2e m to the p plus p minus 1 out of everything. Then what we're left with in our sum is 2 to the 0 plus 2 to the first plus 2 squared all the way up to 2 to the p minus 1. And we've got another 1 at the end. And if you remember your geometric series, the thing in the brackets is exactly 2 to the p. So we've got 2 to the p plus 1, and then an e, and then an m to the p minus 1. Another thing we need to notice is our nice rectangle. If L is the length of the shortest side, then diameter of R is the length of the diagonal of R. Let me draw you a little picture here. So here's a rectangle in 3 dimensions is a box. Elementary geometry would call this a rectangular prism, but we don't bother with that. Then the diameter is at most the diagonal, the distance from, say, this corner to this corner. And that's each side has length at most 2L, 2L, 2L. So the length of the diameter is less than or equal to Pythagorean theorem. One for each dimension. So this comes out to 2L times the square root of P. So the diameter of R to the P is less than or equal to 2 to the P, P to the P over 2, L to the P, which is at most that constant again, 2 to the P, P to the P over 2. L is the shortest side, so this is at most 2 to the P, P to the P over 2 volume of R. Let's wrap the whole thing up. We can put this all together. Now, the upper sum of 1 over the rectangular cover P, it's less than, we had our epsilon over 4 wiggle room. Then sum over all the rectangles in Q4, the volume of the Jordan set J sub R, which we've worked out what that is. It's the volume of R times F of C. Then we've got quite a mess. That diameter of R to the P, that's 2 to the P, P to the P over 2, volume of R. Well, it's less than that, but that's a nice upper bound. We've got a 2 to the P plus 1, M to the P minus 1, and then an E. And then we'll split this sum up into 2 parts. Epsilon over 4 just kind of hangs out front. And then C is a point in R, so we can replace this by the supremum of F in R. Doesn't matter, it'll only make it bigger. And then let's see, this whole mess of constants, 2 to the 2P plus 1, P to the P over 2, M to the P minus 1 E. Then we've got the sum over all rectangles in Q4, the volume of R. Actually, I can go ahead and make this the sum over the rectangles in Q3, because every rectangle in Q4 is contained in a rectangle in Q3. They're non-overlapping, so sum of the volume of the rectangles in Q4, that's at most the sum of the volume of the rectangles in Q3. Let's recognize a couple of these things. Epsilon over 4, then the upper Darboux sum of F over Q4, and then whole mess of constants. Then we've got the upper sum of 1 over Q3. That whole thing times E. And if you go back to your definition of E, Q4 is a refinement of Q1, so the upper sum only gets bigger. This is at most epsilon over 4. And how did we choose Q1? We chose it such that the upper sum of F over Q1 was less than the integral over x of f dv plus epsilon over 2. So that's epsilon plus the integral over x of f dv. And if you go back to the statement of theorem part 1. That's all we were trying to prove. We have shown that we can get upper sums as close as we want within epsilon of the integral of the absolute value of the determinant. If you want to look up how f was defined. So here is the next part of theorem 7.4.4. We let X be a compact Jordan set. And we let G be an open superset of X. And phi going from G to RP be continuously differentiable. And this is the direction where we need phi to be 1-to-1 on the interior of X. And then for every epsilon greater than 0, then there is a rectangular cover. P of X such that the lower sum of 1, not of X, of phi of X, of 1 over this cover of P of X is greater than the integral over X of the determinant of the derivative of your change of variables. Minus epsilon, of course. Putting this together with part 1, we get that the infimum of the upper sum of 1 over all rectangular covers P that is at most the integral of the determinant of d phi, and the supremum of the lower sums phi of capital X that's greater than or equal to the that integral. And then by proposition, by an early proposition in section 7.2, where we defined a higher dimensional Riemann integration, we have that the infimum of the upper sums is greater than or equal to the supremum for the lower sums So they must be equal to each other and equal to that integral. So put another way, 1 is integrable on phi of x, which means phi of x is Jordan, and the volume of phi of x is equal to that integral. And the proof of this part 2 will be the homework for this video, but I will state a lemma. It's analogous to the lemma from the last video that we will leave as an exam study problem. And that is that if Y contains a union of Jordan sets, and we might as well, and they are disjoint, then for every positive number epsilon, there is a rectangular cover P of Y such that the lower sum of 1 over P is now greater than epsilon over 4 plus the sum of the volume of the Jordan sets. And you may use this lemma in your proof of part 2 of the theorem.